Okay, hi everybody. So today we're going to go ahead and start on 4.5, which is we're going to start to deal with the dimension of a vector space. Now, this is going to be tied intimately into the basis of a vector space, and that's basically what we're going to talk about all the way through. Okay, so let's go ahead and jump right into it. So dimension theorem 4.5.1. Let V be a finite dimensional vector space and let V1, V2, all the way to Vn be an arbitrary basis then. Okay, so what's an arbitrary basis? So an arbitrary basis is a set of vectors that is linearly independent and it's going to span the set V. So as it spans it, it's going to basically create whatever that system is. In this case, we're talking about the vector space V. Okay, so A, we have two things here. You have to write kind of small. Sorry about that. If a set has more than n vectors, then it is linearly dependent. Okay, we know that this is the case because in order to create that space, whatever that is, we only need that many vectors to go ahead and create that space. But if you add one more, that's really not adding any more information to the problem. That's just giving you an extra piece on there. So what that means is that extra vector is going to have to be some sort of a linear combination of these other vectors, which would make it linearly dependent. Okay, and then B, if a set has less than n vectors, then it does not span V. Okay, so it's kind of setting this up. It can't have more, it can't have less, so therefore it has to have exactly what that is. Okay, and we're not going to prove this theorem. If you wanted to, that's all in the book. It's detailed in the very back of the book, or sorry, the back of that section in the book. Okay. But we will prove this next one, okay, which is a pretty simple theorem. So theorem 4.5.2, all bases for a finite dimensional vector, okay, so that means has finitely many vectors in it, space have the same number of vectors, okay? You can see how this basically sets it up right here, okay? Here it says it can't have more, here it says it can't have less, so therefore it has to have exactly it, okay? So proof. Okay, so if we have a set S, which is the set of vectors v1, v2, all the way up to vn, is an arbitrary basis for v. Remember, you can have more than one basis in there. Okay, then the linear independence of S implies that any set in V with more vectors than n is linearly dependent. And we say, I'm really just restating this above theorem. And we say that any set with fewer than n vectors, I don't know what I'm doing there, spelling vectors, does not span V. Okay? Therefore, unless a set has exactly n vectors, it cannot be a basis. Okay, so have exactly the same size. Okay. Definition 4.5.1. So I go ahead, I have this whole entire thing in here. So the dimension of a finite dimensional vector space V is denoted by dim V, so dimensions. Okay, and is defined to be the number of vectors in a basis for V, because we know it has to have exactly whatever n is, whatever it is, it's going to be exactly that. In addition, the zero vector space is defined to have dimension 0. Okay, now here's some other familiar vector space. So if I have Rn, okay, the dimension of Rn, anybody want to take a guess? Very good. I'm sure some of you guys would say n, right? If it's 2 space, we know that 2 space can be defined by 2 different vectors. Okay, the dimension of Pn is equal to, it's tempting to say n. Remember, Pn is a set of polynomials that go up to degree n, but you still have that constant term. So it has to be n plus 1. Okay, and then the dimension of some matrix that's m by n. Okay, so what will that be? So it's a little bit trickier to view what it is, okay? But remember, what it is, it's a set of vectors that can go ahead and create that space. So if you have a space of n by n vectors, what's the basis of that set going to be? We've done this before. When we first deal with matrices, we talked about the vector. So actually, let me go over here. So we talked about the vector. Let's deal with 2 by 3 matrices. So I have 1, 0, 0, 0, 0, 0, and then I had the vector 0, 1, 0, 0, 0, 0, and then so on, right? I just continue to write these out, 0, 0, 1, 0, 0, 0, and then 0, 0, 0, 1, 0, 0, and 0, 0, 0, 0, 1, 0, and then the last one 0, 0, 0, 0, 0, 1. Okay, we know that this set of vectors both spans it and this is m, rows by columns, so 2 by 3. And I know this set spans this, and I know that these are linearly independent. So there are 6 of these. There's 6 of these matrices that will go ahead and create Mn. So this is Mn, and I'll write a little multiplication sign in there so you realize what it was. Okay, so that's going to be the dimension of M and N. Okay, so if you have S, which is a set of vectors V1 through VR, it's a linearly independent set in a vector space V. Okay, so you have this set, and it's a linearly independent set within inside of there. Then S is automatically a basis for the span of S. That should make sense, right? If you have 2 vectors and you span everything it could be, then that's the basis for it, especially since it's linearly independent, okay? So therefore, the dimensions of the span of S is equal to how many vectors it has in it. Okay, page 106, or sorry, not page 106, example 4.5.3. So find a basis for and the dimensions of the solution space of the homogeneous equations or system. Okay, so I'm going to go ahead and leave this to you guys to solve. You have lots of different ways to solve this now. You can put it in matrix form. You can use MATLAB. You can do reducer echelon, Gauss-Jordan elimination. We have all these different tools to use to solve this. You can do this on your own. I'm not going to do this for you. But when you do this, you will end up with some sort of a set. You have x1 is equal to s minus t. You have x2 is equal to s. x3 turns out to be negative t. And then x4 is 0. And x5 turns out to be equal to t. Okay? So what that gives us, and by the way, right now you should be having an idea of what the dimensions of this is going to be. Okay, so we're looking at the solution set here. And we're saying, what is the dimension of the solution set? So my solution set can be written as x1, x2, x3, x4, x5. I'm going to view this as a set of vectors, which is equal to so I think I had the wrong thing in here. I need to double check. I have an extra negative in either x1 or the other one. So I just have to double check which one is which. And we could go back and actually go through and solve this, but I have it right here. So why do more work than is necessary? Okay, so this is the mistake. The solution set, this should be a negative s. Okay, so negative s minus t. So this is going to be negative s minus t, comma s, comma negative t, comma 0, comma t. Okay, that's what the solution set is going to look like. So let's figure out what the dimensions of this is going to be. Well, you can see I could rewrite this splitting it up in terms of the s and the t's. So if I have s, so I have negative 1, 1, 0, 0, 0, and then plus t times negative 1, 0, negative 1, 0, 1. Okay, so what you can tell here is that these two vectors span the solution set. Okay, so negative 1, 1, 0, 0, 0, and the vector negative 1, 0, negative 1, 0, 1 span the solution set. So it has dimension 2. Okay, because it's able to be created off of two different things. Okay, next page. Okay, so I'm good? Okay. Just losing my pages here. Okay, plus minus theorem. It's kind of a weird name for a theorem, right? So you have two different things here, A and B, and we're not going to prove either one of these, okay? I'm not proving whole lot in this section today because I don't know if it's worth all of our time. A lot of the proofs are the same, and they're mostly just explanations, which I go through and do anyway. So I'm going to skip over quite a few of these, okay? So if S is a linearly independent set, and if V is a vector in big V, that is outside the span of S. Okay, so you have a set S. If you span it all, and then you have this another random vector in V, if you take that and you add it to S, then it creates another linearly independent set. Okay. Then the sets S in union with V, that one element V. Okay, so you're taking the set S and you're adding on the vector V to it. That results by inserting V into S is still linearly independent. Okay, and hopefully it's pretty clear to see why. Because if it doesn't lie in the span of that, so say you did the span of two vectors and it turned out to be a plane. Okay, so you have a plane, and then you have this other arbitrary vector that's sticking out of the plane, or not going parallel with the plane, but it's going some angle to the plane. Then you can see that vector is not going to be a linear combination of the other ones. And by adding it to it, just going to add to the span of it. So it will be a linearly independent set. Okay. On the contrary, so that's the plus part. Okay. What about the minus part? Okay. So if V is a vector in S that is expressible as a linear combination of other vectors in S, and if S minus V, okay, so now you're taking it away, denotes the set obtained. I'm going to run out of room here. By removing V from S, then S and S minus V span the same set. Sorry, span the same space. So you're right. The span of S is equal to span of S minus V. Boy, sorry about that. I didn't leave you very much room there. Okay. Okay, so example 4.5.4, show that P1 is equal to 1 minus x squared, P2 is equal to 2 minus x squared, and P3 is equal to x cubed are linearly independent vectors. Okay, so we should take note that S, which is equal to P1, P2, is linearly independent. Okay. So there's no way that we can come up with some sort of linear combination of the two. The real difference here is because those are the same and then these are different. So you can't take some sort of linear combination of the two and make them the same. Okay. Now, since P3, to draw this in here, cannot be expressed in terms of P1 and P2. Hopefully that's very clear why. This is an x cubed and those only have x squareds. It can be adjoined to S to produce a new linearly independent set, P1, P2, and P3. Okay, that's all A is stating up there. Okay, theorem 4.5.4. Okay, so there's a lot of writing here, so make sure you guys are writing small. Sorry about that. Okay, so let V be an n-dimensional vector space. Okay, so you know automatically it's going to have the dimension of it is going to be n. Well, I mean, it's right here. Okay, therefore you're going to have n vectors in it. And let S be a set in V with exactly n vectors. Okay, so it's one set in there with n vectors. Then S is the basis for V if and only if S spans V or S is linearly independent. So what are we doing? We're actually taking out one of the conditions. We're saying you can't, you know it has to be spanned and it has to be independent, right? But what we're doing is we're actually simplifying to say it only needs to actually be one of them because doing one will imply the other. Okay, that's what this theorem is actually stating. Okay, so here we go, proof. Okay, and like I said, you're going to have to write small. And we have two different things going on here, right? So first we have to show that Well, so first we're going to assume that S has exactly n vectors and spans V. Okay? So what we're doing is we're showing that it spans it, and we're trying to show that it's independent here. Okay, so we just have to show that it's just to show. So we need to show that S is linearly independent. Okay. Okay, so what would happen if it wasn't? Okay, so assume not. So if we assume not, then there's some vector I'm going to call it V in S that is a linear combination of the remaining vectors. Okay, now let's take it out. Okay, so take out V. Okay, so what this means so therefore by 4.5.3b, the remaining set of n minus 1 vectors still spans V. But this is impossible. Because if you go back up here, actually, is it on the other side? Yeah, it's on the other side. So if you go back to 4.5.1, if a set has less than n vectors, then it does not span V. So this has n minus 1 vectors, and since it has n minus 1 vectors, it can't span something with size n. Okay, so what does this mean? This means that S is linearly independent. Okay, this I know. Okay. Okay, so then we have to show the other portion. Okay, then we have to show the other part. Okay, so we're going to assume that S has n vectors and is linearly independent. Okay, so we have to show that S spans V. That's what I need to show. Okay, so back to this. So assume that S has, what we're going to do is we're going to go the other way now. So what we're trying to do is we're trying to show that if it is linearly independent, then we'll show that S spans V. Okay, so how do we do this? We basically are going to do this by contradiction again, just like we did up here. Sorry, I just have lost my notes real quick. Okay, so what we're going to do is we'll assume not. Okay, that is S does not span V. Okay, so what does that mean? It means it's missing at least one vector, right? That's going to actually span it. So what we're going to do is we're going to add. We're going to take that one vector. So we're going to take the vector V and insert it into S. So therefore, by theorem 4.5.3a, we know that the set this new set is still linearly independent. And has n plus 1 elements. But by theorem 4.5.1, which one was that? A. This set is not linearly independent. Okay, so therefore we know, because we assume that it didn't span it, so therefore S spans V. Okay. Okay. Basis by inspection. Inspection is basically stating, let's look at it and let's come up with an answer. Okay, so by inspection, explain why V1 is negative 3.7 and V2 5.5 from a basis of R2. Okay, we know that it's the same size, right? There's two elements, V1 and V2, and it's R2, so it's going to be R2. So we know, we see that negative 3.7 is not a scalar multiple of 5.5. So therefore it's linear, therefore it's a basis. So therefore linear, or independent, I should say. Independent, therefore a basis. Okay? Just going through and taking a look at there. Okay, and then explain why V1, V2, V3 forms a basis for R3. Once again, you have three vectors there, and it spans R3, so it's of the same size. Okay, so it's essentially the same thing here. But what we're going to do is we're going to take first, we're going to look at, consider V1 and V2. Okay, this forms a linearly independent set in the XZ plane. Why is that? Well, if you notice, these are both 0, which means they're not anywhere in the Y direction. Okay. And V3 is outside of the XZ plane. Okay, so theorem 4.5.4 states that V1, V2, V3 is a basis for R3. Okay, and then that's it. Okay, last page. So the last page, I think, is just, just don't have too much for you here, just a little bit. Okay, so the first one is theorem 4.5.5, let S be a finite dimensional vector space. Okay, so it is a vector space, finite dimensional. Okay, A, if S spans V, but is not a basis for V, then S can be reduced to a basis for V by removing the appropriate vector from S. It's kind of a restatement of the same thing we've been dealing with. Okay, so it spans V, but it's not a basis. That means it has too much. Okay, there's like some overlapping things that are going on. So if you take that one out, you can then make it a basis. Okay, B, if S is a linearly independent set that is not already a basis of V, then S can be enlarged to a basis for V by inserting appropriate vectors in S. Okay, it's once again kind of just a restatement of what we've been dealing with. Okay, and then the last one, theorem 4.5.6. If W is a subspace of a finite dimensional vector space V, then W is finite dimensional. Okay, that should seem pretty obvious, right? If V is finite dimensional, then and this W is the subspace, then that should be the same thing. The dimension of W is less than or equal to the dimensions of V. And then C, W is equal to V if and only if the dimensions are equal to each other. Okay, we're going to do a little bit of a proof, but not too much. We will prove B only here. Okay, so we're only going to do B. Okay, so by part A, W is finite dimensional. And so we write S is equal to the set W1, W2, all the way up to WM. Okay. So it is either, so S is a basis for W or not. Okay. One or the other. Okay. It's going to be basis or it's not a basis. Okay. If so, then the dimension of V is equal to N. But that's by the definition of a basis. Okay. Which means dimension of V is equal to the dimension of W. That is, yeah. Okay. Okay, so that's if it was. If not, then S is a linearly independent set. That can be enlarged to a basis for V by part B of theorem 4.5.5. But this implies that the dimension of W is less than the dimensions of V. So therefore, combining this with this gives me the dimension of W must be less than or equal to the dimensions of V. Okay. And there we have section 4.5. So if you have any questions, please let me know. And we'll see you later. Take care, everyone.